Hello, everyone. My name is Spencer Lee. I welcome everyone to today's webinar for Adapt Builder version 2019, and happy holidays to all those folks there today. Today we're going to cover some of the main features in this new version, Builder 2019. And before we begin, I'll just make a few announcements. Number one, if you don't mind, please keep questions to the Q&A period at the end of the meeting. There is a chat box. If you want to ask questions, if you don't have a microphone, you can type the questions into chat, and I will cover those questions pertaining to the webinar at the end if you guys are okay with that. Also, we will record today's meeting. It will be placed on our YouTube channel, youtube.com/adaptsupport. And there's a webinars playlist there where you can access the webinars that we conduct for the different programs that we offer. So the last announcement will be updates. So if you have not yet updated to this version of the software, we are currently working through updates. You can always send us an email to licensing@adaptsoft.com or support@adaptsoft.com to request an immediate update to get that process started. We do update clients on a staggered basis. So if you haven't seen anything yet, it's coming. We have to control the release in terms of being able to turn around the updates in a consistent fashion. So, but if you want to get updated to this version immediately, just let me know. You can also email spencer@adaptsoft.com. So today what we're going to cover are just some of these new features for Builder 2019. We're going to talk about design strips and splitters. There's been several improvements made to more rapid generation of design strips. The usage of splitters, for those of you who have used the software, this is kind of a pain point in learning the software, I think, and especially in developing your tributary regions. So this has been greatly improved. The use of splitters has been really whittled down to just bounding off the width of a tributary, and we'll show that. We're going to talk about new options for generating and modifying design strips. Also, effective flanges for beams. In this version, you have the ability to model a beam and also to utilize the effective properties of that beam for the purpose of the design of the sections passing through the beam. So that's a new feature we'll talk about. Design strip graphical reinforcement. There are now options to show provided, required, base reinforcement, as well as just the area of reinforcement per area of the section, just the row value for reinforcement. Then we'll go into more global analysis, where we're going to show how the program handles Pdelta in terms of entering that into the model and what types of results do we get for Pdelta. Those get into the graphical reporting options for drift and moment amplification. And also for drift, this is relative to both first and second order Pdelta analysis. We have the ability to produce some nice reports in Excel now for drift and displacements. The last few things we'll talk about are just the modeling of ramps. How are ramps handled? What are the limitations with ramps included in a model? We've made a few improvements. This is more of an ongoing project. I think you'll see even more improvements made for punching shear in the next release as well. This is basically a stopping point, but there's been a couple of new improvements for punching shear, and then the ability to calculate losses, long-term losses, and produce kind of batch reports for felt 3D. So essentially you can model all of your tendons in Adapt Builder, specifically Adapt Floor Pro, and you could use this program to calculate the long-term and the short-term losses and produce reports for those losses. So if any of you are familiar with Adapt Felt, that's just a standalone program that calculates losses. Essentially, we've embedded Felt into Adapt, where you can process more than one tendon at a time for purposes of checking tendon losses. So we'll go ahead and get started. The first thing we'll talk about are the design strips and splitters. And one word of caution: if you're going to be using the new version and you open an existing file in the new version, if you have a lot of splitters in that file, I would the first thing I would do is I would delete them. Okay, so splitters, the way they've been used in the past, is no longer, and so there's a potential that splitters that are opened in the latest version, that they could actually cause, harm to the generation of the support lines, or the generation of the design strips in this new version. So we're going to go ahead and use this multi-story model for the main portion of the webinar. And I'll go to single level mode. We're going to just go to a two-way slab here. We'll look at something fairly simple. I'll use level 3 as my example. And in this level, we're going to talk now about strips. We'll go over to floor design. And in the previous version, I'll reference the previous version just as a matter of comparison. We generally would use the create X and Y strips just to manually generate strips, or we could use what was the old strip wizard. In this particular version, the strip wizard has been removed and it's been replaced with this dynamic editor. So you still have the option to modify or create support lines using these same tools. The difference being, if I just create a few support lines here, you'll notice I'm doing something that would be likely a no-no in the current version, and that is I'm not going to add any splitters to this model, to what I've just added. When I generate the strips, the program now can determine where these strips end, so I don't need any splitters that bound the, let me go ahead and open this markup tool. I don't need splitters that really bound off the ends of the support lines that terminate within the slab boundary. That's no longer required. The way splitters work now is splitters really just dictate how wide a design tributary is along the length of the splitter. So if I wanted to limit, for example, this strip right here along this path, so that the strip really was only this wide, let me change that color to pink, maybe it was this wide, then I would just add a splitter along that path, and the program interprets that splitter, and you can see it terminates the strip at that location. So splitters by and large will be used excuse me, in openings like here. If I don't want anything to go on in this opening, I could use splitters and just add a splitter right there, maybe along these lines, and the program would terminate these strips at those splitters. So splitters are still functional, but they're not required in kind of an intensive way that they have been in the past. Now, if I go ahead and dump these support lines and splitters, I'll go over here and just select these from select by type. And I'm now going to generate strips using the new dynamic editor. So this editor will go through each of these different options. We have first the wizard. This is now where the wizard resides, and the wizard allows you to just create a construction line, and if you pass it through the supports, the program will just generate the strip. If you want the program to snap near the end, at the endpoints of walls, you just need to snap near the endpoint of a wall. Okay, and that snaps back to the endpoint. Here, if I take this and I just snap to the center of wall, it's only going to snap at that point where I snapped inside the body of the wall. So in this case, I might pause this and say, well, that's not what I really wanted. I'll go back and do this the proper way and snap near the endpoints. And now I have that snapped to those 2 points at the end of the wall. If you don't snap at the wall whatsoever, then what happens is we just ignore the wall. So I'll pause this again, come back and redraw. If I go through column 1, 2, and then just go over here to column 3, the program doesn't care about that wall. It doesn't do anything at the wall. So make sure you're snapping excuse me, at the ends of walls or at somewhere in the body of the wall if you want it to pick up the wall as a location where you add a support line node. Go back here, and I'll draw that one back how we would recommend, which would be, again, something like this. Okay, and then we can finish this off in this direction. There's the next two, I'll switch over to the Y direction, and I could do this on one full path. If everything gets cut, it will pick up those as supports. If I don't want this support line to exit the slab at this angle, then what I can do is just click here and then vertically up like so, and that will realign it perpendicular to the edge, or I guess in the orthogonal direction in this case. Okay, and then we'll do the last set of columns here, and that's the generation of support lines for this example. Now, I want to avoid having the cuts go through the openings, so I'll use an X splitter, and the splitter I'm just going to add along this path and over here along this path. Oops, let me back up. I'll just snap on the corners of those walls, and then I'll use Y splitters to bound out the other direction. Okay, and the Y splitters are interpreted by the Y support lines, the X splitters are interpreted by the X support lines, and when I generate my strips, this is what I end with. And if I isolate those, you can see there's very little correction needed to be made in this case. I mean, these are nice support lines, usable support lines without having to go back and iterate through multiple corrections using splitters. So the only splitters we have are really to bound out this opening in this core area. Now, one other item that's useful in the dynamic editor is this wall item. In the program, if a design cut extends over a wall, the program, if it's a post-tension slab, for example, we don't report stress when a cut extends over a wall, and we actually don't design that section for strength reinforcement. For any strength load combination, it's only designed for service or minimum reinforcement. So let's assume that we don't want these cuts to extend over this wall. I have two ways of handling this. First, I could just leave the strip as is. The support line passes through the wall, and there's this new option for wall boundary. And what this option does is this allows us to add boundary conditions for walls relative to the generation of strip, the generation of the design strips. If I say for this wall here and here in the X direction, I do not want the program to cut the sections over the wall. So I'll go ahead and just say, I'm going to select user defined. I'll define these as an X only boundary. So I'll just click on the wall and specify the boundary. I'll close that. When I regenerate the strip, notice that the program creates a very small section over the wall automatically. You would have had to do this with splitters in the previous versions of the software. And notice it sticks out some tiny distance, and then the sections above actually extend all the way down to the wall. So this is one way of handling this, but I might say, well, this integration line is too long. I don't want to integrate a section that long. So that's fine. We can just take this support line and just move it slightly outside of the wall. So once I have a support line away from the wall, but the wall is still a boundary, and I regenerate, now I get a cut down towards the face of the wall, but I don't get anything over the wall. If you still wanted to have results over the wall, I would have to add another support line along here. Okay, so this is an example of how we can define wall boundaries to our walls so that the program doesn't cut strips over these wall locations. One example this core example is probably not the best example that illustrates this, but if you had a wall, let's say away from, let's say you have a wall here. See if I can get that properly input. I'll turn off my snap tools, come back to it. So I'll just add a wall right there. And we want a support line over this frame line, a support line over this line here that we've added. I'll actually move this back down to the wall location. And I just don't want this wall to be cut by any of the sections from above or from the sections below. So I can just go and define that wall as a boundary. I'll come back to the floor design under dynamic editor and say I want that wall to be a boundary for, again, the X direction. You could assign X only, Y only, X and Y, or I just say no boundary. I'll just deal with it manually through use of splitters maybe. So I'll define that as an X. And again, if I regenerate the strips, the program just cuts out away from that wall. You'll notice this big gap right here. The reason there's a gap there is because this wall is also a boundary. So if I need to go ahead and deselect that as a boundary in this case. I'll go back to user define and say this is no boundary. And now when I generate the cuts, these now extend up to this face of wall. These extend down to this face. So for wall intensive models, this may be helpful when generating the cuts and generating the strips for your slabs. A few other options in this dynamic editor: limits. This just allows you to check the criteria of the support line. So rather than having to double click and changing the criteria, I could just change the criteria here. Maybe I want to change these all to one way. So I'll just Windows select or select the different support lines. That's probably not what I want, so I'll go back to two-way. And you can also enter a limit of tributary width on both sides of a support line. So if I say I want this to be limited to 5 feet, this support line here, let me make sure okay. I don't know why that's not, oh, I need to select that, forgot to do that. So there's my 5 foot limit. And when I regenerate this strip, this just gets limited to that distance on either side of the support line. This might be useful if you're doing middle strip and column strips in the same model, and you want to force the tributary width to either side. The last option in the dynamic editor is under display. So this really just displays criteria, direction, and limit. And I can update that, and that will just show up on the drawing so you can see what you have specified for your support lines. Okay. We'll now talk about beams. Something just happened while I turned my head away from that. Let me go ahead and open that again. Okay, we'll talk about how the program will handle the beams. If I have a beam along a couple of these frame lines, let's go ahead and model 2 beams here. So I'll go from here over to there and something like this. And going back to the dynamic editor, at beams, if we use the construction line and we snap near the endpoints of the beams. Now, if I snap at point 1 and all the way over at point 2, it's not going to work because these beams are actually segmented. There's actually 1 and 2, so I need to snap near point 2 of beam 1, near point 1 of beam 2, and then point 2 of beam 2. And then out. The program will break this up. So this strip becomes a 2-way slab strip. The next strip is actually a beam strip. This becomes a beam. The program just classifies it because it recognizes the beam. The nice thing is we do not need any splitters. So coming back to my example from earlier, in the previous versions of the software, I would have to add a few splitters here to make this beam stuff work out because I stopped points inside of the slab boundary. In this version, that's not required. You can see this becomes 1 beam strip. This is another beam strip. And this becomes 2-way slab and 2-way slab. So For beams, the program also gives the ability to design the beams using effective properties. So the integration length for this beam is from here up to the edge of the slab. But if I wanted to limit the actual design and the stresses and the different output that I get for the beam design, I could take this beam and I could say I want to go into general options and use effective flange. So this uses ACI and European code effective flange, depending on what codes are selected. With that selected, you can choose whether or not you want to include the contribution of both post-tensioning and reinforcement outside of the effective flange for the rebar calculations. So those options are shown here. If I store that, and I'll just run through a quick analysis of this floor. So let's analyze here for strength dead and live. And I need to remesh, I forgot about that. Beams are in place, I added those, so there was already a mesh there. If you add components, you should remesh the slab. Okay, and then I'll go ahead and analyze. And I'm going to design this beam number 1 and beam number 2. So I'll select those only and design those. You'll notice for beam 1, I had selected effective flange. Let me reset the view here. So when I go into the design sections, you can see that the actual integrated length is 145, the effective length is 63.5. So the program is using the effective properties based on that effective flange to design this and to calculate stresses. For this beam over here, the length is 151 and the effective length is basically 151 also, because we're not using effective flange for this beam. So that option is available now in the software. If we go up to plane 6, you can see this is a level that has a lot of beams. So we could still use the same dynamic editor functionality. We just have to be a little more careful on a level like this, where when I'm snapping, this is a continuous beam, so I can snap near point 1 and 2 of this beam. This beam is broken up into 2, so if I want the program to automatically break this up, I have to snap on the interior points like so. And then I might, do a wall location. I'll just do another beam location and so on. So you could use this to generate strips even in a grid structure where you have a lot of beams. It might be a two-way slab with beams on all frame lines, or it could be a one-way slab with beams and so on. So this is a nice tool. It really saves a lot of time once you get used to using that in generating your design strips. Okay. We're going to show one more thing related to single level. I'm going to go back down. I think we were at plane 3. Let me make sure. Yeah, plane 2. So at plane 2, let's go ahead and just design. We already have a solution stored for this level. I ran it analytically in single level mode. I'll come back to it and I'll actually design all of my strips. One thing that's new for reinforcement is if we go over to the result browser and under design sections, there's this new option called reinforcement right there. It's under investigation. This option will show me the graphical area of still on all of my support lines. So the required area of still for this combination strength is shown graphically in this view. We have top rebar, which is green, bottom rebar is blue. And I'll go ahead and use my settings to change the font height. So this is a nice graph if you're interested in seeing how much reinforcement is needed at certain locations in the slab. I could toggle between X and between Y. I only have X now in this slab, but you can also check the provided reinforcement. So if I want to know, well, this is based on what's required per calculation, but what's the reinforcement based on required or based on provided, based on what adapt has shown me and put in the slab. If I select this, it says generate the rebar for this combination. So we need to generate the rebar first. I'll go here to calculate, generate for strength, dead and live. Once I've done that, you'll notice what happens to the graphs. They get linearized. They're not based on a per point basis. If I go now and select this, and I'll turn off the first option, this is what's provided. So you can see if I overlay those, these bars get stretched out by the program, so there's a lot of reserve over on the sides at the bottom, where I'm hovering my mouse. And this is a nice way to just check where you have demand and where the program is adding reinforcement as well. You can look at base reinforcement. If I added, for example, a bottom mat of steel to this slab, I'll go ahead and do that under rebar. We will add, actually, let me close out of that. I'll select the slab, use Mesh Wizard, and I'm going to do a bottom mat of number 5s at 12, let's say. Once that's done, I have to redesign the sections to capture that new rebar in my design cuts. So I'll redesign my sections. And now if I look at the base, this shows me the area of steel in each section per the base rebar. I could go back to calculated. This would be in addition to base. So you can see these two graphs actually dropped quite a bit because now we have this amount of base rebar in the section and it's adding this amount of rebar on top of the base. And then finally, you can look at the percentage of steel in the section. This is for the calculated rebar. This is not for base reinforcement. This is per calculated rebar. So it would basically be equivalent to the required rebar divided by the area of the cut. All right, so those are some of the changes we've made that are, I think, more applicable to single level mode. We're now going to transition into multi-level mode. So let me go ahead and clean the screen here. I'll move this thing out of the way. I'll just keep those beams, that's fine. And we'll switch over here to multi-level analysis mode. We're going to first talk about Pdelta. So the program now considers second order analysis, big Pdelta, I'll say, and we do not use the iterative method. We use a non-iterative approach where we calculate a geometric matrix and use that for the solution. If we go to load combinations, you'll note that there's now a new option here, which is called Pdelta. So whenever you mark a combination Pdelta, the program is going to check, and it could potentially take longer depending on how big the model is and how you set the combinations up, and I'll describe that. We have two ways to really frame the combinations. We can run singular solutions for each Pdelta combo. I'll call it S, and we can run batch solutions called B. Singular solution would mean that if all of your Pdelta combinations are unique, meaning they may have the same load factors for gravity, but they have a different load factor for a lateral load case, the program would actually solve each one independently, meaning it would have to converge on a geometric matrix 3 times in this case. If you want to run this in batch mode, the program allows you to do that if you set the combinations up a certain way. The combinations are not required to be in sequence, by the way. I'll describe that here in a moment. But in this case, we have what's called a master combination right here. This is master PDM1. And that basically is just my sustained factored level gravity loads. So we have 1.2 dead plus 1 live. And you'll note that I have 2 additional Pdelta combinations, PDSX and PDSY. Those have identical load factors as the master combo. The only difference is we add a EQX and an EQY. So when the program sees this type of arrangement where the master really only includes factors on the gravity loads, but the other combinations have the same factors, the program solves the geometric matrix for the master, and then it reapplies that to these other combinations with EQX and EQY. And so it doesn't have to solve the same matrix 3 times, it solves it once, and then it can essentially solve these last 2 with the same matrix in place. So again, if you do not want this to be solved that way, you want it singularized, I could actually just remove this, and then the program would just, you know, do these 2 independent of each other. By me adding this PDM1 combination, I can then batch process those load combinations. You can have more than one master combination. I could have another one. I could say I want PDM1 and then I want PDM2. And in this case, I might, you know, do 0.9 times dead load, and then I would do PDSX2, PDSY2, and I'd have 0.9 again in these cells, and maybe I do 1 and 1 again, or 1.2 and 1.2, whatever the combination is. You could have more than one set of master and secondary combinations that the program can process. They do not have to be in order. The program just simply scans. If all of this was filled up with combinations that were all set to Pdelta, the program would just scan those and determine which ones it can lump in batches, and then it would process. If they're all unique, you would have, you know, 10 to 15 combinations being solved independently. So that's how you set the combinations up. The next thing is what types of results can we get from the Pdelta? Well, Pdelta results can be used for column design. They could be used for wall design. They're just like any other combination. You're just getting amplified actions for those combos. What you cannot do in the current version with a Pdelta combination is you cannot design slab strips or beams. You can review the actions for Pdelta, but we actually suppress the design of sections for these combinations. The combinations are still only designed for service and strength, not for Pdelta. Column design and wall design can be designed for Pdelta, but not floor or beam designs, basically design strips that you set up in the model. Actions can be viewed for those strips, however. So there's a couple of other nice features here. I'll go ahead and just close that. And we're going to run the analysis of this global structure with the Pdelta combinations in place. So we'll go to analysis. I'll just select my set of combinations. Now in the codes, usually it references you to running Pdelta at the point of overload, or below that point, let's say. And so that means you probably would run Pdelta with cracked stiffness modifiers for your components. In this case, I'm not doing that. I'm just using uncracked. But you can use usage cases in the program to set up a set of modifiers that you would want to run and process the Pdelta combinations for. Just an FYI, we have that capability. That was released back in, I think, 2000 and maybe 15, maybe even before that, 2012. But that's available. Here I'm just going to run it as uncracked. We'll go ahead and solve this model. This model takes just a minute or so to solve. If anyone has questions while this is solving, this may be a good time just to maybe dump some of those in chat, and I'll see if I can pick up 1 or 2 of them now. Otherwise, we can sit here in silence. So. Once this is done running, we're going to talk about the graphical results that you can gain from these Pdelta combinations. And And those are mainly over here under analysis, column, drift, and moment. So we're going to talk about drift and moment amplification factors that we can check graphically for these elements in the model. This mesh, I meshed this model at 7 feet, so that's a pretty coarse mesh, but the model runs fine. It's stable and no issues there. But if I was actually doing this for design, I'd probably back that down to 4 or 5 feet for the mesh, or even less. Okay, this is done. Now what I'll do is isolate my columns to show the graphical results. Okay, we'll go back to visibility, default display. I want to get rid of all those elements, and then I'll go to column design and just isolate the columns. And I'm going to go to the roof level, plane 28, and we'll do single level mode here. There's one question here. So if the question says, if I remember correctly, for usage modifiers, you had to adjust E to modify ICR and strong direction of the wall. Is that still the case? Yes, there's no current modifier for wall bending about the S axis. That's the strong axis. So if this is a wall in plan, we have R. I'll do it this way. We have a wall. This is R, and this is S. If that wall rotates, the axes rotate with it. So bending about S, we have no modifier for that. I believe we have modifier M11 and M33, which is kind of about the Z axis. Steve, that's coming. That's something that we're aware of, and we need to add that in. So it's been documented as a priority item for global mode. I can't tell you when, but it has been documented. So back over here at the result browser, if I go to column drift, you'll notice that if I have a combination selected that is not Pdelta, these amplification factors get turned off. That's also the same for moment. If I go to action, moment, here the amplification factors get turned off. The amplification is judged against, it's basically code checked, if you will, against these values in display. I have maximum moment amplification and maximum drift amplification. They're defaulted to 1.4. This just might be an indication of the stability, if there is a stability problem in the structure. So you can modify this, user define this value for your amplification factors. If I do select a Pdelta combo, so in the loads table, there's a new classification called Pdelta, and let's say I pull out Pdelta S in the X direction. So this is seismic in the positive X direction with some like torsion, I think 5%. And having selected that, if I go back, now you'll see that these actually get turned on. So the program will report, for this combination selected, I can report the combined drift, which is really just the global displacement, differential top and bottom. I can look at the X direction, Y direction independently for this combo, and I can also look at amplification factors. So for second order to first order ratio of drift, what's the percent difference? And you can see at this level for combined amplification, it's 4%. If I look at individual directions, you know, it will update that result to show that value. And we can do this globally too. If I turn on the entire structure again, I can check my amplification here. The amplification is actually okay. This is all under 1.4, but the well, for this combination, it's not. Let me see if I update that. I'll go back here. Yeah, right here, this flags it as no good. So it's the Y direction that was flagging this value no good. The X direction looked, let's see, we're in the Y direction now. or the Y direction load, PDSY, and then the other one's PDSX. So these get updated as you select the different combinations. And then the maximum values are shown here. So we have some location where the ratio of second order to first order drift is for the Y direction is 50%. That might cause alarm, or the user to go and check that and see where that location is. And all of the columns will have a value for that ratio. You can also check bending moment amplification. So bending about R and bending about S. We can check again for any Pdelta combo. What is the amplification and moment between first and second order analysis? This doesn't directly tell us what the actual moment is. Clearly, I could say, well, for this combination, if this is 15% over and this is moment about R, I could turn on moment about R, and it would stand within reason that if I took the value and I decreased it by 15%, that would give me the first order moment. Or one thing I like to do with these combinations is I've set up two combos, seismic X and Y, which correlate to PDSX and PDSY. These would just be my first order solutions. So I could go and select, this is, let me go to a wireframe view. Actually, I'm gonna navigate down a couple levels here. This is just easier to see the moments, and I will go to wireframe, so under visibility. Okay, so this is the moment about R for PDSX. If I go to amplification, this is 1%. If I come back, moment about R, and just switch the combination over here to one of my first order combinations that I had set up, you can see this is 182 and Pdelta was 184. So really, really close. Just showing you how you can investigate some of the results, because the amplifications are just a little bit indirect. If you're wanting to see actual moments, you have to have a combination that has produced those results for you. So those are some graphical results that we can obtain from just the Pdelta and the second order analysis. You could also go to column design, and if we go to design settings, you still have the ability now to design directly from these Pdelta combinations. So rather than using moment magnification, which was something that our partner program S-Concrete was using, moment magnification for non-sway frames, it actually relied on second order analysis for sway design. And now we can satisfy that requirement, where you can set up your Pdelta and directly design for the actions relative to those combinations by just simply selecting them in this dialog. The process is the same. There's another question here. Is it usual to use walls and frames with beams to resist lateral action due to wind and earthquake? So the question is, I mentioned earlier that we do not design beams for the Pdelta effects. We do, however, report the actions. So the question is, how can the beams be designed to consider lateral actions? If you want to design the beams for Pdelta in a primarily sway frame where they're participating in the lateral analysis, you would have to take the actions out of ADAPT and design them outside of the program currently. Or you can determine the amplification factor, for example, and scale up the factors on the first order combinations to get that same moment. I mean, there's different ways you could quote unquote trick the program to do that, but I think we're on par with other programs in the same space, that in the sense that I don't know exactly what other programs are doing, but I know we did investigate it, and for the most part, we found that primarily the vertical components, the columns and walls, were being designed with the Pdelta, but not necessarily the the beams. But I agree, Giordano, the code is pretty specific. It says the beams, you need to account for the secondary actions in the beams or the second order actions in the beams. It was just a programming decision at the time we developed it. So with that can be changed and improved as time goes on. Okay. Drift, there's a new report available for drift. Under reports, this applies to both first and second order. This is not necessarily, you don't have to run Pdelta to get this report. You could do it otherwise just for first order. So under analysis data, drift report, this will allow the user to select the combinations you want to check. And I'll just check one of these for sake of time here. But if I take that PDSX and I set up my allowable code check values for allowable and amplification, I can then select my directions. This will dump a PDF, or excuse me, an Excel report for my structure. Now this is some good information that has been difficult to obtain in the program previously. So the first thing, I'll kind of describe each one of these tables and charts. The first thing that we show is from top down, every column and the coordinates of the columns and the story height. So if you're ever looking for column coordinates for any post-processing of data, you can always come here and dump this report. This will show you what those coordinates are. Displacements, these are just the raw displacements for the combination that I selected. So at column 251, plane 28, for the combination PDSX, I have top and bottom, X and Y, and global displacement shown here. So these are just the raw displacement results. The drift at columns, again, the same structure to the table. We have the list of columns top down, the load combination name, and then we take the drift, the differential in the X direction between top and bottom. If we take this displacement, 8.67 minus bottom 7.91, we would obtain 0.77. So that's drift X, Y combined, and then the percentage. This is this value divided by the story height in a percentage form. So if any of these values are exceeding the allowable, we show the status check here, no good. And you can go down the building and look at your columns for this particular combination for this example. Average drift is basically taking all of the columns at a level and finding the average. So we just take the average drift for all columns in X, Y, and combined directions, and also check drift per the story height again, per the average. So this is an average value. Maximum drift envelope, this would be just the maximum at each level. So here we're just showing a percentage. This is just represented as drift, maximum drift at any level for X, Y combined. Average drift envelope would be the envelope of combinations. So I only selected one combo, therefore the average drift envelope and the drift, these really would be the same because I've only processed one combination. But if you had 50 combinations, this would give you a better view of what's happening relative to all 50. And then if you do run Pdelta and you select a Pdelta combination, we show the amplification table here as well for X, Y, and combined amplification of drift between the first and second order based on this Pdelta combo. So this is much easier to check. In previous versions, all of the drift checking had to be done through the code check or through trying to obtain displacements based on the slab contour or the column displacement points graphically, which is still there. I mean, it's still useful, but we just offer another option here to obtain some of those results. Okay, so that's Pdelta and drift in a summarized form. The next thing we're going to talk about is ramps. The program can handle ramps to a degree, okay? And that degree is that the program does not design ramps yet. You can model ramps for purposes of just analytical consideration. We cannot design the ramp, we cannot add post-tensioning yet to the ramps, or they're really there just as a model component. So in this case, let's assume we have this parking structure, and if I go to a side view, there's 4 or 5 levels here, and I basically want, you know, a ramp on this side and then a ramp on the opposite side, something like this. So, and I might want to do this because I need the continuity of the ramp for purposes of lateral analysis in the program. This was really hard to do in previous versions. You would have to simulate it through stepping and connecting elements, and it became tedious to manage that and to make it work properly. So let's go back to a plan view, and I'll navigate back to level 2 here. When I go to model, there's this new option for ramp. The first 2 points define the top of the ramp, the second 2 define the bottom of the ramp. So I'm at level 2, which goes down to ground. And if I select, for example, point 1 and point 2, and then at the bottom, point 3 and 4. Notice when I go to point 4, this actually gets locked because the ramp has to be planar. It can't be warped. So we lock out this last point, and there's my ramp. Okay, this is actually going from level 2 down to ground. If I go to the opposite side, I want this ramp really to go up, or actually to go down the opposite way here. So we're going to go, and I'll do this the opposite side. I'll go from here over to there. Oops, let me try that again. The snap tool is a bit sensitive here, so there's the ramp on this side. Now, if I go to a 3D view, this is currently what my ramps look like. Nothing, you know, too spectacular, other than you can model the ramp quite easily now. And I might want to copy those up. So if I just take these and copy, they're like any other component. Let's see if I can move that point. So I'll take these 2 ramps and I'll copy them vertically. So we'll go to visibility, or excuse me, to modify, vertical copy up, and I'll copy these up 3 times. And now if I go to multi-level mode, I have this structure which has ramping on all levels. Now let's say we want to introduce a beam along the edge of the ramp, or a beam transverse to the ramp. Let's do both. So if we, and I'll go back to single level mode, level 2, to model this. So I'll first model the beam transverse, and we'll go to beam, and we're going to model that across here. Now I'm modeling at level 2, so the beam is really not in the plane yet of the, it's not dropped down to the plane of the ramp. It's still at level 2. And I'll also add something that looks like this. And I'll show this on just this one level here. Okay, so if I go to a 3D view, you can see, by the way, I'm going to select those 2 ramps. If I right click, there's now hide and show selection. Just, you might be interested in that. I'll hide that, and I can right click and show all. So that used to be done only through visibility. That's now a right click option. We're adding more options there. So notice these beams are actually above, you know, I want them to be aligned with the ramp. So what I'll do is I'll just select the components. I'll go over here to model, and I'll say connect to ramp, and those get automatically connected down to the ramp component. Okay, and we'll go back to visibility, and you can see those elements shown like so. The program was also modified to be able to handle the meshing of the beams that drop down below the midpoint of the column. That was an issue when you were trying to step ramps in simulation. So we've done a lot of work on being able to handle the meshing of the ramp and being able to handle just the analysis of the ramp. But ultimately, the ramps are there only for analytical purposes. If you try to draw a section cut, if I, for example, draw a support line along here, the program will automatically just cut that off at the ramp. You wouldn't have a section cut that goes through this space. So these are kind of treated as openings, automatic openings when we look at them for purposes of design cuts on the main slab. We're going to move over now to punching shear. So for ACI, specifically for ACI, if I go back to my other model, let's go to this two-way slab model, and I'll go ahead and let me turn off some of these options for display. Okay, we'll take this level, for example. If we go over to floor design, shear design, there's two new options, or actually three, that have been added. There's this option for consider critical section outside of the shear reinforced zone. If you boil that down, that just means the program now checks critical sections based on this octagonal shape. In previous versions between ACI 3.18.11 and prior, the program would always use a rectilinear shape for all critical sections. The program now has the ability to calculate it based on this shape, which is explicitly required in ACI 3.18.14 based on your rail arrangement, which is hard-coded into the program like so. So if we have this rail arrangement, the program or the code says you have to check the least critical section at d/2 in this pattern, and this option would allow you now to do that. This edge distance to rail or stirrup line is just the distance from the edge of the slab to the rail, or to the it's actually to the center line of the studs in this case, or the center line of the stirrups. Question about the ramps. Let me just pick this one up. Will the beam under the ramp be designed for the self-weight of the ramp as well? If we could design the beam under the ramp, it would. The program considers all self-weight, so the self-weight of the beam is considered for the analysis. But again, Anasoya, even the beams at the ramp would not be designable in this current version. Anything connected to the ramp is there only analytically, not for design. There's also an option here to apply minimum reinforcement for drift. So if you have seismic requirements where you have to reinforce for punching shear, you have to reinforce within 3.5 square root F prime C. The program allows you to check that also. That's this option, apply minimum reinforcement for drift. We have a new technical note that covers all the details of this, these two checks, but if you select those two checks, those are just applied to the general punching shear analysis that had been improved in the previous version, 2018. And so you may want to go back and review some of those notes and that technical note. If you're interested, we can add that too. I believe it's on our website now, but if not, you can contact support at AdaptSoft and obtain that. Okay, the last thing we're going to look at is felt 3D. And let me go down to level, let's go down to level 2. And at level 2, actually let me go up to level 3. I'll turn on my tendons here. So if I double click on a tendon under stressing, you can see this stuff here has been added. Even if you were using calculated force method in the previous version, the program would require the user to enter a lump sum long-term loss. We now can consider that specifically per calculation of long-term losses if you select this option. If you go back to effective force, both of these get turned off if you use calculated, and you have the PT shop module enabled. Right here I have the shop module enabled, which is just part of the splash screen. That's shown right here. If that's enabled, then the user can choose to calculate the long-term losses. If that option is disabled, you can still only use estimate lump sum loss for long-term. Once you've actually gone through and specified whether you're using calculated or not and whether you want to calculate the long-term losses, you could check the friction and elongation, and then we have reporting options here to basically produce a report for the long-term losses. It's similar to the felt report. It's just been updated and modernized into an HTML format and also a PDF format. So I'm not going to produce it here because I have several tendons. It will take a little too long to produce, but this allows you to produce the report for your long-term losses. So that's the content that we were going to cover today. I'll go ahead and open it up for any questions that anyone has. So if you don't mind just typing the question into the chat box, see what we can do about getting those answered. If you don't have any questions, I appreciate everyone's attendance. Again, happy holidays, and you're always welcome to contact us at support@adaptsoft.com for questions that might arise on specific projects with any issues you have with the software or just feature requests or feedback. Okay, no questions. Oh, there's one. Yeah, Sam, the ramp would be considered part of the overall floor diaphragm. So you would have some continuity based on the fact that there's a ramp connecting one level to another for general lateral analysis. I guess one of the limitations and drawbacks is really the ramp provides you just with a sense of raw analytical results. When it gets into design of those other components, then you have to, especially at the ramp level, you would have to use other means to design the ramp. But analytically, it would be considered as part of a kind of a continuous multi-level diaphragm, if you will. Another way to answer that, Sam, would be you would see lateral, lateral action in plane, lateral action in the ramp element for a lateral analysis. Other questions? If there's no other questions, I'll wait here another minute or so just to see if anything else comes up. If not, again, you're welcome to exit and then you can pick up the recording at youtube.com/adaptsupport if you're interested in the recording. The question is, do I recommend running the Pdelta with a master combo? I would say yes. Typically, if you're going to be running Pdelta, that would mean you're going to have a multi-story analysis anyway. And for the most part, the geometric matrix is driven largely by the sustained load in the axial, tension compression forces in the vertical components. Those are affected somewhat by the lateral component, but not to a great extent typically. So the master combination option just gives you the ability to process the data faster without without a lot of loss, let's say, in accuracy or the level of results that you need to complete a design with respect to code requirements. So, and a lot of times these big multi-story projects tend to have a lot of combinations and a lot of nodes. So, you know, that this one is a little bit streamlined, this model example, but when you get into something that a user has built, they tend to be a bit more beefy in terms of computational time and requirements. All right, I appreciate everyone's time today. If you have any questions outside of the meeting, feel free to contact us and we could explain or confirm anything that you had questions on. But again, happy holidays and thank you.